temperature, pressure, amount or size. For the part on history development, we will start with the history of temperature development. In 1714, Daniel Gabriel Fahrenheit first invented the mercury in glass thermometer, and in 1724, he also introduced the Fahrenheit scale. In 1742, Anders Celsius introduced the Celsius scale, also known as the centigrade scale. In 1848, William Thomson proposed the Kelvin scale, which is based on the concept of absolute zero. Next, the history of pressure development. When Galileo Galilei discovered that water pumps could only rise 34 feet, scientists became interested in why this phenomenon was unable to be explained. Evangelista Torricelli discovered that his pump's water draw limit was due to air pressure, leading to the invention of the mercury barometer. Then, the Pascal pressure unit was developed as a result of the observations made by barometer inventor, Blaise Pascal, who found that atmospheric pressure increased as he went down mountain. For the history of size development, John Dalton's atomic theory, based on experiments and observations, proposed that matter is composed of atoms, which combine in fixed ratios to form compounds. The definitions. For temperatures, temperature is a physical quantity that represents hotness or coolness in a quantitative way. Next, pressure can be defined as the physical force exerted on an object. The force applied is perpendicular to the surface of objects per unit area. Object mass is a measure of the amount of matter contained in an object. Small samples of certain types of matter will have small masses, while larger samples will have larger masses. Now, we move to the theories of temperature. Temperature measures the average kinetic energy of the atoms or molecules in a system. Temperature is also an intensive property. Temperatures in SI units are provided by the Kelvin scale, which we denote with the letter T. It is an absolute scale based on the concept of a lower limit of temperature known as absolute zero. In thermodynamics, the zeroth law states that if two systems are both in thermal equilibrium with a third system, then the two systems are in thermal equilibrium with each other. For instance, if A is in thermal equilibrium with B, which is in thermal equilibrium with C, A and C are also in thermal equilibrium. Moving on to the theories of pressure, Pascal's principle, also known as Pascal's law, is a concept in fluid mechanics that applies to both gases and liquids. It asserts that within a stationary fluid confined in a sealed container, any change in pressure within one segment is uniformly conveyed to all parts of the fluid in the container's boundaries. This is the 3D model of Pascal's principle. When dealing with fluid pressure, descending deeper results in a greater volume of water situated above, consequently leading to an increased weight and an associated rise in water pressure. With any fluid, the pressure will be higher at the bottom of the container than at the top. There are three measures of amount the size of a homogeneous material, which are mass, number of moles, and total volume. These two equations can calculate the number of moles. Total volume is a defined quantity given as the product of three lengths. These are the questions that are related to volume. Now, let's take a look at an example of the calculation regarding the related formula. A cylinder with a piston contains a certain amount of air. The cylinder has a cross-sectional area of 0.02 square meters, and the piston has a mass of 5 kg. The cylinder is filled with air at a density of 1.2 kg per cubic meter. The height of the air column in the cylinder is 2 meters. The question then asks us to calculate the pressure exerted by the air on the piston at the bottom of the cylinder. To calculate the pressure exerted by the air on the piston, we can use the fluid pressure formula, which relates pressure, density, gravitational acceleration, and height. Thus, the pressure exerted by the air on the piston is 23.53 pascals. Next, given that if the temperature is 300 K, the question asks us to determine the number of moles of gas based on the ideal gas law. We can use the ideal gas law equation. We can find the volume by multiplying the area by height. So, the number of moles of gas is equivalent to 0.0032 moles. Last but not least, the question wants us to find the required force to compress the air to half of its initial volume while assuming the temperature is constant. Now, we want to compress it to half of its initial volume, so the new volume is 0.02 cubic meters. The pressure will change as well. Using the ideal gas law, P2 is 47.06 pascals. Now, we can calculate the force required to compress the air to this new pressure. So, the force required to compress the air to half of its initial volume is approximately 0.941 newtons. This is the calculation by using MATLAB. And that's the end of the video. Thank you.